our last speaker for the day and the workshop, actually.
This way.
Will be Julia Moriarty talking about the role of local resuspension on oxygen exposure time, something that did come up a few times.
Okay. Thank you for letting me be the last speaker of the day. I stand between you and lots of discussions. For those of you I haven't met, I'm an assistant professor at the University of Colorado in Boulder. And if you've seen me give a talk before, you know I usually talk about very coupled hydrodynamic sediment transport by geochemical models, much like some of the ones we've seen today. Today, I'm actually going to take a step back and talk about a simpler approach to try to estimate oxygen exposure time and the role of resuspension on oxygen exposure time. Uh-oh. Oh, there we go. Okay. And so the motivation for this is a slide or a figure that just trying to understand how much carbon is, when we think about how much carbon is buried on deltas, Kendall showed this figure yesterday, and it shows that if you look at a sediment accumulation rate, the fraction of carbon that's deposited on the seabed that's buried versus remineralized increases as you have higher sediment accumulation rate. And this is, however, you have these group of sites here, then that's the deltas, right? So you have half an order to an order of magnitude less carbon burial efficiency compared to these other sites in the ocean. And this is thought to be due to repeated cycles of resuspension and lateral transport that expose this organic matter to oxygen in something called the suboxic fluidized bed reactor. Since this paper has been published, there have been studies linking variations in organic matter properties to qualitatively to changes in resuspension and oxygen exposure time, as well as I've found one lab study that links resuspension frequency to changes in the remineralization rate constant. However, linking this oxygen exposure time to rates of remineralization, which is something I'm interested in as a modeler, it's something that our models are very sensitive to. Kendall mentioned this yesterday also. Is somewhat hampered by our ability to calculate oxygen exposure time in the marine environment. And so in order to do that, so historically, how we've calculated oxygen exposure time is from Hilary Hartnett's paper. And so she estimated this just thinking about the seabed, where if you have sediment being deposited at the top of a core, and she's calculated the amount of time it takes on average for a particle to go from this top of the seabed to this, from the oxic portion of the seabed into the anoxic portion of the seabed, or in other words, how long it takes it to transit through this oxygen penetration depth. And in order to estimate that, that's been estimated by dividing this oxygen penetration depth by the sedimentation rate. And so, of course, this estimate neglects things like resuspension, lateral transport. However, we know in the coastal environment, this is not always a great assumption. You're looking at the same site that Stanley showed you earlier on in the presentation. This is from a site that's about 25-meter water depth offshore of the Rhone River. And here you're looking at bed shear stress over a period of 2 months. And then this is modeled erosion, modeled seabed elevation. So every time it goes down, you're getting erosion, then up it's deposition, erosion, deposition, erosion, deposition. And then this red line shows your oxygen penetration depth, which is about 1 to 2 millimeters at the site, even during these erosional and events. And so one of the things I want to point out is that, at this site, this is just one example of a site where you're getting erosion of centimeters of erosion of anoxic sediments and organic matter that's being suspended into a relatively oxic water column. And so this is, of course, adding to the exposure of that material to oxygen. And so how can we account for this? And what is the role of resuspension on oxygen exposure time? Does it add 5%? Does it add 200% to our estimates? In order to do this, I'm taking these time series of seabed elevation and then translating that. So we look at each layer, vertical layer of the seabed, and how frequently the material in that layer is suspended. And so we get a profile that looks like this, with the x-axis being the resuspension frequency, and then the y-axis is depth into the seabed, So near the surface, you get more frequent resuspension, and then that decreases to 0 around a couple centimeters into the seabed at this site. And you can see that, for a portion of the time, we have resuspension of anoxic sediments into the oxic water column. And if you integrate under that curve, that's my attempt at drawing integration in PowerPoint. We do actually integrate, I promise. If you integrate under that curve, you get the resuspension-induced oxygen exposure time. And if you can add that to the oxygen exposure time that Hillary Hartnett proposed, the oxygen exposure time not due to resuspension. And if you add those together, you'll get what I'm calling the total oxygen exposure time. Okay, so the question is, how much does this matter, right? And so one thing I'm going to, so the main result here is that if you look at the oxygen exposure time without resuspension, so that's what I'm showing here in black, it's about 0.02 years at this particular site. And then if you account for the resuspension induced oxygen exposure time, that approximately doubles at this site. I'm showing you 2 bars here and 2 profiles here because we calculated it 2 different ways. We already had a really calibrated model set up, the hydrodynamic sediment transport model that we worked with Christoph's group to validate and to do. And then, however, also out of many sites, this isn't available. So we also used Rouse profiles, which I'm happy to talk about later, as a way to extend this to so it could be extended to other sites relatively easily. But no matter how you calculate the seabed elevation profiles, you get similar profiles and a similar amount of resuspension-induced oxygen exposure time. One of the nice things about models, so as Stanley showed you, if you vary the environmental conditions, you get different estimates. And so here you're looking at the fraction of oxygen exposure time due to resuspension. So 0 would be no resuspension. Resuspension isn't contributing at all to oxygen exposure time. Blue is it's 100% resuspension. And so this is on the x-axis, you're looking at resuspension frequency factor. So that's a factor by which we multiply these profiles by. And so if you multiply them by 2, you're doubling the frequency of resuspension. If you have 0, you have 0 resuspension. And then on the y-axis, you're looking at oxygen penetration depth. So we're going from 0 to 2 centimeters at the top. And so what you see is what you would expect is that as you increase resuspension frequency, you increase the amount that contributes to oxygen exposure time. And then also as the oxygen penetration depth becomes thin, if you keep resuspension the same, you're going to more frequently resuspend anoxic sediments into the overlying water column just because your oxic layer is thin and there's not as much sediments in it. And so then you would also increase the fraction of oxygen exposure time due to resuspension. One thing I want to point out is that this fraction doesn't actually depend on sedimentation rate because we are assuming a constant sedimentation rate. So the sediments moving through both the oxic layer and the resuspendable layer at the same time, at the same rate. And so that doesn't affect this, but it would, of course, affect the total oxygen exposure time, as well as the resuspension-induced oxygen exposure time in like seconds or years, whatever unit you're using to measure that. And so here you can see that as sedimentation rate increases for both total oxygen exposure time and resuspension-induced oxygen exposure time, you get lower. So as you have faster sedimentation, the organic matter transits through the vertical seabed quicker, and you get lower oxygen exposure time. And then a fun note that I don't think I have time to explain. I have a little bit of time to explain. Okay. Is that for the oxygen penetration depth, as it gets thicker, right? We talked before about how as it gets thicker, you're going to decrease resuspension-induced oxygen exposure time, but you also are actually going to increase the total oxygen exposure time. It's a little bit of a different effect because overall, as you expand the thickness of that oxygen risk layer, it's just taking longer for sediments to go through to translate through that oxic layer. And overall, that's the bigger effect compared to the impact on the resuspension-induced oxygen exposure time. One thing I will very, very quickly mention is that in addition to the Rhone site, we're doing this for different idealized environments. So we're using sine curves to represent tidally influenced deposition and erosion. We're accounting for near constant wave erosion and deposition, and then event-driven erosion and deposition using Gaussian curves. And that's, so you can start to look at like how big does an event have to be to influence the oxygen exposure time as much as like a, continuously resuspended tidal site, for example. And at that, I'm out of time. I will say, I think this is motivating future work, and my movie doesn't work, but it is motivating future work to incorporate this into a more complex biogeochemical model to try to get some better constraints on this as well. And with that, I'll end it there.